Today, I'm going to teach you how to build something which could literally save your life. I'm going to show you how to make one of these. A high-power taser that has the ability to drop an assailant in a matter of seconds, but only if you have enough power. It takes about 100 watts to put somebody down, and in order to achieve that, you have to have the right parts. Lucky for you, almost everything you need you can find inside of consumer electronics, if you know what to look for. Parts like batteries, power semiconductors, inverter transformers, rectifier diodes, capacitors, spark gaps, pulse transformers, final stage capacitors, and some kind of case to stick it all in. For the difficult to find components like pulse transformers, I'm going to show you how to make one of these from scratch that'll outperform almost everything else that you can buy. With that being said, let's get started. This schematic will act as our guide. Since this is a complete tutorial, we're going to cover a bit about each of these parts and where to find them. I'll throw some annotations on screen now if you want to jump ahead or there's something you already know. Well, let the hunt begin. For these two resistors, you can use just about anything between 200 ohms and 400 ohms. Today I'm going to use 220. A quarter watt is more than enough. You can find Zener diodes in just about everything from televisions to microwaves. These Zeners are going to protect the MOSFET gates so a high voltage spike generated by our output transformer doesn't get kicked back and blow out the gates. You can use anything between 10 volts and 20 volts. You'll also need a couple of MOSFETs, like these ones here which were removed from computer motherboards. If you look on the front of each FET, you can find some writing if you look real close, and you just type the number followed by the word datasheet and you can find it right away. This one is good for 75 amps, and we're only using 7.2 volts, so the 25 volt rating is plenty for us. This one here is only good for 30 amps. That's not enough for what we're doing, even though it has a 30 volt rating, which is still high enough for our 7.2 volt battery pack. Computer motherboards, really the best place to find these, but you can find them in a variety of other things like power supplies and CCFL inverters. Here's the board layout I've been using. I really like this design because you only need a Dremel tool with a cutting disc and some blank PCB to make it. This is where the components are going to be placed. And these green dots indicate where you'll make your solder connections. Pay extra attention to the large heatsink tabs on the MOSFETs. Sometimes it's difficult to get enough heat onto those tabs and get solder to flow underneath them. It usually helps to add a little bit of flux or tin the pads first. Now let's cover inverter transformers. These are CCFL inverter boards, and you find these on the back of flat screen televisions, the older ones. Now modern screen TVs use LEDs. Older TVs used to use really thin fluorescent tubes, and they were powered by these high voltage transformers. Now each of these transformers takes in somewhere between 12 and 28 volts, and it generates about 2,000 to 3,000 volts output, and we're going to remove the original primary coils. We're going to have to cut open this case because it's in the way, so we can't unwrap those wires. So we'll just slice straight around with a razor blade. Got a mark on there, and then we'll score it a couple times so that we can eventually snap through it. Alright, so I actually have a completed unit that I finished up earlier. The primary coil has been replaced. There are now 10 turns on this primary. They're center tapped, so there's 5 turns on one side of the center tap, 5 turns on the other. The ends of those turns are going to the circuit board that we made earlier. They're going to the drain of each of these two MOSFETs, and the center lead is going to be hooked up to the positive terminal of our battery source. I've attached these two arc over wires. They're separated by about 1/8 of an inch. You have to have some sort of discharge gap, because if this transformer is powered by this circuit and it's open, you can have internal arcing. Alright, let's hook it up and see what it does. Instantaneously, a nice hot arc. This transformer generates high frequency, high voltage alternating current. Alternating current is not useful to charge capacitors. We need to convert it into direct current. To do that, we're going to use a full wave bridge rectifier. This rectifier here is made of 4 of these 12,000 volt diodes. Here are some other diodes that you can find inside of older televisions. These ones are also rated for 12,000 volts. And if I were to configure them in a bridge rectifier assembly, AC goes in here, and positive comes out here, negative comes out here. And here's with the rectifier attached. The AC output wire from the transformer goes to this point, and then there's another white wire from the transformer output that wraps around to the back of this rectifier. And then here is our positive output and our negative output. Let's talk about caps and gaps. You'll need a high voltage capacitor. Maybe one like this, which is a 470 nanofarad 1000 volt cap. Or maybe one like this, which is what we'll use today, a 390 nanofarad 1000 volt cap. You can usually tell the ratings based on the numbers that are on the outside. This one's obvious, 0.39 UF, which is the same as 390 nanofarads, 1000 volts. Sometimes they're not quite so straightforward, like this one here, which is a 470 nanofarad, 1000 volt cap. Though it doesn't say 1000 volts, if we look up this model number, the PHE 450-1000 by RIFA, the datasheet does verify that it's a 1000 volt cap. This polypropylene cap looks similar to the other two, but we can see here it says 275V. The ratings on this capacitor are no good for tasers. If you have enough of these 275V caps, in our case we would need 4 of them to get a 1000 volt capacitor, you can put them in series, but you have to make sure that the capacitance value is the same. Spark gaps are a handy way to discharge the capacitor into the pulse transformer. If you look on the sides of each gap, you can usually find some ratings. Like this one here says ST102. Well, the first 2 digits here are the value, and the third digit is the number of zeros you add after it. So this would be 1000, a 1000 volt gap. Some gaps just have the numbers or the value written straight on the side to tell you what they are, like this one here, which is 350L, a 350 volt gap. Or this one, which is what we'll use today, a 1780 volt gap. But there's a problem. Our capacitor is clearly only rated for 1000 volts DC. The lucky news for us is I've tested this cap, and this can safely take 2000 volts DC. According to the manufacturer, it also has a quite high pulse rating. Don't assume your capacitor can take more voltage than it's rated for until you test it. Polypropylene capacitors like these are really nice because they have a self-healing capability, meaning if you blow them out, and you'll tell if you do by a little cracking sound, you can still use them. If you can't find a spark gap, you can also make one by using a piece of circuit board and taking a Dremel to it to cut out the center. Here's just 2 wires soldered to those tabs, and this works really well. Figure about 3000 volts per millimeter. This spark gap here was pulled from a wireless cable modem, and this spark gap here was pulled from a furnace ignition power supply. Alright, now we're going to cut the core for our pulse transformer. We have a piece of 1.5" nylon rod centered in the chuck and ready to go. That material looks like this. I picked this up at my local plastic supply warehouse. I have also used, and this in my opinion is the best material that you can get for winding your own pulse transformers. This is glass fiber nylon rod, and it has the highest insulation factor of any of these common plastics. And this is the tool that we're going to be using today. I made this out of a 1/2 inch wide, 1/8 inch thick piece of tool steel. It's cut on the belt sander. You can see I've grooved it down. It's 2 millimeters wide at the tip. It has a very flat, sharp edge. .24, that is close enough for what we need. finish it off, we're going to use some pieces of fiberglass strand that are just pulled off a fiberglass sheet. And here's our completed pulse transformer. When the epoxy was finished curing, I sanded up the sides just to make a little more space inside the taser unit itself. And you can see it's hollow straight through, so we're gonna put a primary coil like this one inside of here. It's made out of this silicone wire and a ferrite rod from a computer power supply. I finished wiring the driver circuit off camera, but I'll go over the changes I made real quick just so you know. I added some copper cooling pads to the drains of both the MOSFETs. That's going to give some of that thermal energy a place to go and give us a slightly longer duty cycle. I've also added this MOSFET, which I'm going to connect to this little switch, which will go inside the case. That allows this very small switch to control the 30 to 40 amps that are going to flow into this circuit when it's operational. Micro switches come in a lot of different varieties, but just about any momentary switch will work just fine. Large, small, gold? Yeah, they come in gold, and that's what we use today. These are from a projector, and I like them because they're really, really flat, which allowed me to squeeze one into a case in a place where I otherwise couldn't fit a switch. The purpose of these capacitors in our circuit is to store up charge from the pulse transformer and release it in one big burst. They'll increase the peak output current quite a bit, but in consequence they'll decrease the peak output voltage. Now these are sort of rare to find these days, but were quite common in the tube radio era. If you are trying to find high voltage capacitors that have at least a 10 to 15 kV rating, you'll have to find old transmitter equipment. If you can't find these, you could feasibly do something like this. These are 3 kV caps, and there's not quite enough here to do the trick, but you could take some capacitors and put them in series like this, and then insulate them in some kind of material like epoxy or hot glue. Here's our capacitor unit. It's 3 15 kilovolt capacitors, just these guys, chained in 3 with a piece of plastic wrapped around them, and then the extra epoxy I had from winding the transformer I just poured into this case, giving me a nice insulated layer, and here are our 2 output leads on the ends. That slips right into the case real tightly like this, and it's going to attach to that piece. This is just a plastic insulator that I cut out so that we can get some more insulating material between our output transformer and our other components. If we don't do this, it's very likely a spark will jump across the gap and create a problem for us later down the line. we can probably go ahead while this circuit is out and glue this MOSFET down in place too. Time to install the switch. Let's go ahead and solder the switch onto the circuitry. In order for that switch to be pressed, all of this stuff inside moves at once to press it. That means this top plate, capacitor bank, pulse transformer, spark gap, and other capacitor are all glued together as one big moving assembly. The rear switch has been installed and a temporary battery is connected, so let's give this thing a try and see what it does. A little bit of pressure on the front plate should activate the switch in the back. And voila! Beautiful. If you look real closely, you can see the motion of the switch. Let's talk about batteries. This can be a tricky subject because good batteries are hard to find. The ones we're using today are 150 mAh, 3.7 volt, 30C. We're going to put the two of them together in series, just like this, so we can get a 7.2 volt battery pack out of these. Now 30C at 150 mAh gives us a continuous rating of 4.5 amps, which is far short of the 30 to 40 amps that we need. The good news is that these batteries will safely supply 40 amps as long as you keep the duty cycle low, in our case 5 to 7 seconds at the maximum. Even during 7 seconds of operation, they'll get quite warm, so as long as you give them time to cool down, they won't suffer any damage. Common batteries, like this one from an MP3 player, even under dead short, can't really supply much more than 10 amps. E-cigs contain a single cell battery like this one. This is a LiPo battery, 3.7 volts, 1 watt hour. These batteries are good for about 10 amps apiece. So, in order to supply yourself 30 to 40 amps, for short duty cycles you need 6 of these. 3 in parallel, and that's in series with 3 more in parallel. That will give you the necessary current. You can also use these. This is a single cell lithium ion from a laptop. In a pinch, you can get away with using 2 of these batteries. To keep our batteries healthy, we'll use one of these generic battery protection circuits. This is about $2 on eBay, but you can also find them in anything that has a LiPo or lithium ion 7.2 volt battery pack. I've taped those 2 batteries back to back and wired them up to one of those protection circuits and installed it into the taser, which you can see here. In order to charge it, I didn't have much space for a charging port, so I just used one more of those gray pieces of plastic and installed one of these tiny little pin headers, which is from an LED strip controller. What I've done here is connected the 2 outside pins to negative, and the center pin is positive, so no matter which direction you insert the charging port, you can't reverse it. And here you can see I've mounted the taser to a makeshift leather gauntlet. This gauntlet was simple to construct. It's just cut out of a piece of sheet leather using a pair of scissors, and a special type of hot glue called amber melt was used to hold these Velcro straps in place. It works well, it's hands-free, and all you've got to do is push forward. Hey, thanks for checking out the video. I really hope you guys learned something. If you like what you've seen here, please be sure to subscribe, and if you have questions for me or ideas for other videos, please leave me a comment below. I will go through and read those comments. Until next time, enjoy these outtakes. So much editing. Cool. Cool. This is the weirdness going on in the lab right now.
Sorry everyone, I cracked up because I thought it was a genius, and you see what happened is I wanted to solder, but I wanted the solder to be close by. Fortunately it kind of grabbed me.
Where is that transformer of yours?
It's around here somewhere, Jeremiah. In the meantime, look at this transformer.
Yeah, we're not at all ready to power this thing up. Soon.
What? Like, this is great. And then, like, it soldered on, and I was like, uh-oh, now I'm attached to it, and it had me by the finger.